Hello, Andy Kettle here once again from Servo Components and Systems here in the UK to take you through some of the features of the Copley Controls amplifier range. This time we're going to set up a drive for CAMIN to demonstrate some of the features of the internal CVM program and its CAMIN capability. So to do that we've got a Xenus XCTL drive in this case, but it could be almost any of the Xenus or Copley range of amplifiers, the XCTL for instance, and coupled to that we've got a Rockwell MPL A430p motor, but it could be any motor, and it could be even linear as well if you so wished. So I've shown in other videos the data you need to enter to configure the motor and to tune it, so that's going to be a given for this video. And the only connections we've got to the Xenus drive is in fact the AC 230 volt AC in, 24 volt power supply to control the logics. We've got a connection to the motor itself, to the power, UVW, and we've got the encoder feedback. That's all. The enable we've done by frigging the drive, pulling the input 1, which is traditionally used as the enable line, as high clear faults and enable the drive. So I pulled it up for the purposes of this demonstration. So there's no wiring on the I/O at all. But to perform CAMIN you need to enter a CAM table or tables, depending on what you want to do. So if we just go into setup for one moment, you'll see that I've got it set up. We've got a brushless motor, it's a rotary motor, as you can see in the bottom right hand corner. We haven't got any halls again on this motor. We're just using analog sine cos, which is a 1 volt peak to peak sine cos signal, and we've got it, most importantly, we've got it set in CAMIN mode. There we go, that's how you set it in there. And then the next thing we need to do is enter the CAM table itself. So when you're in CAMIN mode you get this box here for CAMIN, and there's a config page which I'll come back to in a moment, and the tables. So you'll see the number of cams you can have are 0 to 9, so 10 cams altogether, and I've simply created a range of 10 cams with a sine wave in it. It doesn't have to be a sine wave, it could be a square wave, it could be a mod trap, or any sort of shape you want to follow, provided the motor is capable, the drive is capable of doing the power. You know, you've got to be careful you don't put a step move in there that it can't follow, because it will trip. So we've just got some cams with a sine wave in it, and you'll notice if I start off with cam 0, the midpoint is 564, and that will increase. So basically I'll just change the amplitude of the cams as we go through it, so cam 9 being the largest. Okay, so that's the CAM data. Now how do you get the CAM data? Well, you can restore CAM data from a file, and we've got it here, and that is purely a table of master-slave values. First line is the title of the CAM table, and then we've got CAM 0, and then the number of points we've set up in the CAM. And if you go down there you can see all my CAMs. CAM 3 for argument's sake there. So that's how you can import it, and you can generate that sine wave or any other profile using an Excel spreadsheet or some other Visual Basic program you may have written to generate it. So that's that. And then you've got to configure it. So basically the drives are really 1.5 axis drives, in that you've got a separate master encoder input if you wish on the multi I/O port, where you can have step and direction, pulse up, pulse down, full quadrature if you want to follow in another encoder. But in this case, for this demonstration, I'm using an internal master. The other points here, select the CAM table you want to use, and any offsets you might want to put on the CAM. And we've also got it taking control on power up, so we'll start CAMing as soon as you enable the motor. Now this demonstration in fact is going to use a CVM program to select one of the 10 cams that I've just shown you by using a value within a register. So if we close this now and then go into CVM programming, you'll see that I've got a number of programs in here, and the main one is in fact sequence 0. And sequence 0 will run on power up. If I go to, I've shown you this before, but if we go into setup, here you'll see I'm using no BCD inputs, and I'm starting on power up and reset. We're not running at the moment. If I can run it, hit run. It's enabled it. You'll see here we've started to enable it. And in the program, what I've got is I'm using 2 registers primarily. Register 0 is selecting the cam, and register 1 is affecting the speed. So the first thing I do is just reference the home, so the current position is home, but you could do a proper home to a datum switch if you wanted to. And then I multiply the speed by 10, and that's because the actual units within the cam is in 0.1 of a unit. But you could put any modification factor in here, and in fact you'd have to scale it up for the mechanics of the motor of your application. So that would change depending on the application. And then here we've got a range of conditional jumps where I'm looking at R0 to select the cam. So basically the first one, if it equals 0, it jumps to sequence 0, 19. If I go to the next one, it goes to 21, etc., etc. 10 times. So if I go to the first one, point 17, here's my first cam. And you'll see it's using the internal master, and it's using the value stored in R3, which we'll come to in a moment. There's no trigger, but you could use an input for a trigger, or as I said, a master encoder. And here, this is where we select cam 0. And you saw the next one jump to 19, and you'll see exactly the same, but it's now gone to cam 1. All the way down to cam 9. And then we simply jump back to the start, so we just keep looping around this program, changing the cam depending on the value within R0. So it's just a point, we don't need to use registers. You could change it so it uses digital I/O if you wished, but in this application we're going to use the registers, and so for the purpose of this demonstration we're going to use the ASCII line command line editor, and this is where we can write to the registers directly. So at the moment, if we view the registers, you'll see there's nothing in any of them. So if I write, let's say cam 1 to R0, return, we've got a 1 in R0 there, it's popped up. And if I change R1 to, let's say 800, we've now multiplied by 10, which is R3. R3 was the value for the internal clock rate of the internal master. So we can see it's oscillating there nicely. You can see it. Get rid of that window. And on the scope, let's just get rid of these screens so you can see it. We've just displayed the commanded position. Now in this particular application with the camming, their master position is in fact the value of the master clock in the cam. So that's the master position. And because I had it set between 0 and 360, you can see it goes up to 360, sort of, and then it wraps around and does it again. And then on the green, the blue one is the limited position, which is the output from the cam, and the green one is the actual motor position. So that's what you want to follow. The green and the blue need to be closely aligned. So if I change the speeds here, let's put 100 in, you'll see it'll slow down. And just a point though, the way it'll finish the cam before it changes, so it'll do 1 cam. If you change the number during halfway through the cycle, it'll finish. And you can see the plot showing you the new speed. So if we go really faster, gotta be a bit careful here we don't roll off the table. So you can see we can change the speed. If I just go back now to slower speed, and change a different cam to 9. Oh, sorry. The right one. So I'm now selecting cam 1. Cam 8, and you can see the difference amplitude. So that's just following the different values in the cam, the different cam tables. And down here you'll also notice in the control panel it actually tells you which table you're using, so you can have verification that it's actually doing what you think. So we've used this sort of application many times for standalone drives, running vibration tests and material testing, shaking bogies around on a undercarriage of a train. All sorts of applications where you just want to control a vibration. So I hope you found this interesting, and love your feedback. So thank you for watching, and look forward to seeing you again. Until next time, goodbye.